Hello everyone, how you doing? Welcome to Total Immunology today. And today what we're going to be doing is looking at how samples are moved through in a healthcare laboratory setting. We're going to focus primarily on why do we need to get samples processed in a particular way, and we're going to look at the different nuances, particularly around blood sampling. Okay, so we're going to jump straight in and start focusing on what we're going to look at. And what we have to think about first of all is we have to think about why is it important? What is important when we get samples processed? First thing we need to think about is making sure that we get them done in the right turnaround time. It's completely pointless having a super urgent test and then taking 9 days to get the result generated. Likewise, it could also be argued that if the result is not super urgent, and it just needs to be done maybe in time for the next patient appointment, which could be in 2 weeks or 4 weeks' time, it seems silly to battle and nearly kill the system to try and get that result out in 3 hours. Okay, so we have to take into account the pragmatisms of how long it takes or why we need that result in a certain time frame. We need to make sure that all the samples that we deal with are done at the same level of quality, and that quality has to be at a high enough level for us to deem it appropriate. And so that's also a lot of woolly words, I appreciate. Quality is a word we use a lot in healthcare laboratory working. It determines how well we are doing the process, how accurate are we producing a result, how standardized and consistent and precise is it. And there's an awful lot to that, which will be covered in multiple other episodes. The last thing is something we have to take into account, and we don't often like to, and it's sometimes a bit of an awkward or dirty word in the world of public healthcare, but we have to think about cost. We can't do an assay or a test at a point or a way that means that we're going to be spending so much money to get that one result out that we are going to be unsustainable if we suddenly have to do 100 or 300 or 5,000 or 10,000 of them. So we have to make sure that how we're doing this is cost effective. Otherwise, it's not going to be sustainable in the long run if we need to open this up to more people. And so one of the things that we want to focus on here is mainly blood, but just to remind, and this has been talked about in previous episodes, what kind of samples are used, particularly in a blood science lab or an immunology lab, even more particularly. And those three sample types are blood, urine, and cerebrospinal fluid, or CSF. Okay, and the vast predominant sample type that we use is blood by a significant majority. Okay, so we're going to concentrate on the blood side of this, and we're just going to talk about blood because it's not as simple as just blood. Okay, so we take the blood predominantly from a peripheral site on the body, and you can see in this photo here an example of that, but we can sometimes take the blood from more established catheters in a patient, such as a central line. And there are many different types of blood tube that can be produced. Okay, and you can see in this photo just the varied amount, and you can see predominantly three colors in there. You can see a gold, a purple, and a green, and they are the core three types of blood sample that we take. This is only one particular commercial version of the different types of blood tubes that you can take, so I don't really think this is the only types, but we're going to go through these and look at them. And one of the things you have to also think about when it comes to blood tubes is one of the processes that we do on the vast majority of these samples, but not all of them, is to centrifuge them and to spin them. So if you want to think what a centrifuge is, effectively it is a machine that allows you to spin the blood in a circle, to do a revolution with it, and you do it at very high speed. And what you're ultimately ending up with is a situation where gravity will remove through centrifugal force and push the highest mass objects to the end of the circle, okay, and leave the less heavy objects inside that tube to stay in one fixed position. So it allows you to separate out components of that blood according to gravity by forcing gravity to exert itself at a higher foot by increasing the spin rate. Okay, and so what we're going to do is just go through those three main types of blood that we have. And so the very first one that we have, that we often take, is what we call a serum tube or a clotted blood tube. Okay, and we do this to obtain a blood component called serum. Serum is the fluid component of the blood with the clotting factors removed. Okay, so if we have a situation in whole blood, what it actually possesses is many different types of things. First of all, it has cells. It always looks red, and the reason it looks red is because the vast majority of those cells are red blood cells, and they contain hemoglobin in them, and hemoglobin is red pigmented. So you will often see a lot of red in there. But actually, the fluid is mostly water. It has albumin as a main protein in it, and it has loads and loads and loads of different other things in it. It could be hormones, it could be clotting factors, which are small proteins that help the blood clot if it needs to. And there's so all these different things in there. And so when we want to obtain serum, serum is all of those fluid components that don't include the cells, and also the clotting factors have been used up in the blood in order to make the blood clot. So what often happens in these tubes is that the tube environment has been designed to encourage the blood to clot as quickly as possible. And you will start to see, and you can see in this diagram I've made, that the blood will effectively shrink and contract into a solid gloopy gel. And what you're going to start to see is kind of an orangey gold separation from that, which is going to be the fluid left over. The other thing about these tubes, and a lot of these tubes possess, is a gel plug. And you can see in the diagram in my illustration, a gel plug that exists there that sits at the bottom of the tube. And that's important because when you then spin that tube, what happens is that the gel plug becomes a separator compartment between all your cells that are of high mass. So when they are put in a centrifuge, they move down by gravity to the bottom of the tube, and what remains is your fluid component, which sits there. And you will predominantly see these tubes in hospitals that are gold top. That's the vast majority of tubes that are clotted will show that. If it's in a pediatric or a child blood tube, it will be much smaller, and often they are shown as a clear top lid. Okay. So the next one we have is a purple top tube. And the purple top tubes contain a very special chemical in them called EDTA, and I'm not even going to try and say what the true name of that chemical is, but it's there for you. And one of the things about this blood tube is it allows you to do one of two things. It first of all allows you to look at the blood cells because the blood will not clot. And so the reason why the blood will not clot is because EDTA is a very special chemical that does a very posh thing called chelates. Okay, and what chelates really means is it grabs and accumulates lots and lots of different metal ions in a solution and puts them all together in a big bundle. And what it does is it stops those metal ions from being chemically active in the solution. Now, there are lots of different blood metal ions that exist in our blood that are very important, things like zinc and magnesium and calcium. And all of those things are involved in helping your blood clotting. So if you take them out, the blood no longer is able to be able to clot. So this enables you to keep a nice red liquid that contains all your cells floating around in the fluid. And you could use it if you wanted to look at the cells in the tube. So let's say you wanted to put them into a machine and now analyze the cells, you can do that. And we do that. Or you can separate out the cells from the liquid by spinning the tube. But this time, the fluid component is not going to be serum because the clotting factors have not been used up. Instead, what you're going to have is something called plasma. Okay, so very important to understand the difference between plasma and serum. There is one other option that does a similar thing, okay, but is subtly different, and that is what's called a lithium heparin sample, okay, and these are normally green top tubes, okay. If they're in a pediatric setting, they're normally orange or brown. And what they have inside them is another chemical, but this is actually something that's a natural compound that's produced by most mammals, and that's called heparin. And what heparin is designed to do by the body is to inhibit blood clotting. We're not 100% sure how we do that, but what we think it does is it actually activates specific inhibitor enzymes that are involved in the clotting pathway of your blood. And what you can do with this blood tube is, again, if you want to, you could spin it, and that will allow you to isolate plasma from the sample if you needed to, again, because the clotting factors have not been used up. So you would end up with a fluid component containing the clotting factors, which would make it plasma. Or again, you can analyze the blood cells in their kind of natural habitat. But the difference here is in this setting, you have not removed any metal ions from the sample, okay? Because the EDTA, remember, in the other sample collates or grabs the metal ions. In lithium heparin sample, it doesn't. And what that means is that those ions are still available to be used. Now, there are some assays, and in immunology specifically, we do some assays where we want to look at those immune cells in that blood sample, and we want to look at their functionality. We're not necessarily interested in counting how many there are, but we want to make sure they can do the job we think they're designed to do. And if we want to do that sort of analysis, we have to make sure that they have all the metal ions that would exist in blood naturally available to them so that they can operate. If we were to use, for instance, an EDTA tube, and we tried to look at the functionality of an immune cell such as a lymphocyte, we would find that that lymphocyte would not be able to function very well. And that's because it would not have metal ions available to it. For example, things like calcium, which is very important for cells to be able to operate. So now we understand the different types of blood tube that happen. Actually, if we look at the bigger picture of how the lab flow works, and this is just a very basic schematic, because I don't want to spend too long on it, talking about the stages that we talk about in sample analysis. So the first stage is ultimately we need that sample to be taken. We need the correct test to be requested. We need that sample to get to the lab in an appropriate time frame. We need to make sure that the lab receives the sample appropriately. That means we're going to check its suitability. Is it too old? Has it been damaged in the transport? Do we have appropriate identifiers on that sample to definitely tell us it's the patient that we think it is? If there's any doubt, it would be dangerous for us to test it. Once we are happy with the suitability of the sample, we're going to give it a unique identifier in the laboratory. So within the laboratory now, it's going to be given a serial number, and we call that serial number a lab number. And it normally will have a letter at the front or a year, and then it will have a range of numbers. And those numbers may be sequential, we may be counting them, or it may be that those numbers are randomly given and generated by a computer system. Finally, we're going to make sure that sample is now logged in our laboratory computer system, and that's very important. And in another separate episode to this, I will talk about the IT that we use in a hospital system. The next stage is we're now going to analyze that sample. That may not be on the same day, that may be on a different day in the future, and we may have to store the sample in the interim, and we may have to store it in a way that means we can find it. Remember that these labs will have thousands and thousands of samples at any one time, and so they all look the same. They've all got either different colored tube tops on them, but effectively they're not very different from each other. So we need to be able to pick them out correctly and make sure we're going to test the right one. We need to test it on the right test. We need to generate results on it that we believe to be as accurate as possible. So we have to put controls on that assay and check they are good. Once we've got the result, it may mean we have to add on additional tests. Maybe that early test we've done is a screen and it's now indicated further testing on that result. So that's the second stage. And then the final stage is actually creating the result and reporting it. So we've now got the result, we need to report it, we need to publish it effectively and put it back to the person who requested it. We're going to use our laboratory computer system to do that. And we're going to report it on there. Hopefully, we're going to try and use IT as much as possible and reduce how many human interventions there have to be, because for every human intervention in reporting the result, there is the chance of error. And error could mean that we put the wrong numbers in, or we say it's positive when it's negative, or we report the wrong result on the wrong patient. Now, these things can happen. And so we have to try and minimize the chances of that occurring. Those results now need to be reviewed in the context of all the other results that the patient has generated. And they may be the results that have been generated in other labs as well, not just immunology. That might be that all those results look completely normal. That patient can have all their results generated and sent back to the main caring clinician. Or we may have to put interpretive comments on, or we may have to phone someone up because those results may now show something that's very serious and there needs to be action happening quicker than maybe just a routine appointment in the future. Now you can see I've put these into three boxes. I put these into three boxes because we have three very clear stages in this workflow process. And we call them the pre-analytical phase, the time when we haven't started doing any actual experimentation on the sample. We're just trying to ensure we get the correct sample taken and the correct tests asked for, and that the sample safely gets to the site where the analysis is going to occur. We have the analytical phase, which is where we're going to do that work and actually analyze the sample and generate the data on it. And we finally have the post-analytical phase. The post-analytical phase, as we finish generating the data, are we going to appropriately look at that data? Are we going to appropriately report that data? And are we going to carry out all the necessary correct actions based on what that data tells us? And when we're looking at workflow, these are the things that we really care about. And we have to make sure that in each of those stages, we are implementing correct training, correct protocol, coming back to what I've said at the start, making sure that all three of those phases help us deliver a good turnaround time for the test, making sure that we will ensure that we're always producing the right quality for our test and the result. And finally, making sure that all the effort and investment we're making in all of those stages is not making the actual test itself so prohibitively expensive that we've defeated the purpose of doing it because it's not sustainable. So all of those parts need to be considered, and that's what we build into what we call our overarching system of how we make this work. Okay, thank you very much for this. I hope that's been informative for you. Please obviously like, subscribe, and comment. If you want to let me know of any particular aspects that you feel we need to talk in further talks, then please let me know. Otherwise, good luck. Thank you. Have a great day, and I'll see you later. Bye bye.